In matrix multiplication, the row of the first matrix is paired with the column of the second matrix. The pairs are multiplied and the products are totaled or added to give a single number. Let's do an easy example of matrix multiplication to get you into the swing of things. We take the rows of matrix 1 and multiply by the columns of matrix 2. So here I have a 2 by 2 times a 2 by 2, which means I'm going to have a 2 by 2 in my answer. We're going to talk about that in a minute. But a 2 by 2 times a 2 by 2 will give you a 2 by 2. And the position of this answer is row 1, column 1. So I think row 1 times column 1. Row 1, column 1 tells me to do 1 times 2 plus 2 times 6. Here in the answer, I'm in row 1 and column 2. So take row 1, multiply by column 2. That would be 1 times 4 plus 2 times 8. Here my answer is row 2, column 1. Well, that means I'm going to go to row 2 and column 1. I always take the rows from the first matrix and the column from the second. 3 times 2 plus 4 times 6. And here I'm down in row 2 and in column 2. I'm row 2, column 2. That means take row 2 times column 2. 3 times 4 plus 4 times 8. That will give me 2 plus 12 is 14. And 4 plus 16 is 20. And 6 plus 24 is 30. And 12 plus 32 is 44. With matrix multiplication, a key concept is that in order to multiply, the columns of the first vector must equal the rows of the second vector. Here's an example of matrix multiplication, meaning one matrix times another matrix. I'm not talking about one matrix times a scalar. If I have first matrix, row times column of matrix 1 and matrix 1, the column for matrix 1 must equal the rows of matrix 2. Here's matrix 2 row and matrix 2 column. These must equal each other. And row 1 and column 2 on the outsides here will give you your result. For example here, I have a 2 by 3 vector times a 3 by 1 vector. Well, as long as the columns from vector 1 equal the rows of vector 2, which I do have 3 columns from here and 3 rows from here, then my resulting vector will be a 2 times 1, which is the rows of vector 1 and the columns of vector 2. I know I'm going to have a 2 times 1, so I do my 2 rows times 1 column. I know this is row 1, column 1, and this is row 2, column 1. So what is that? Row 1, column 1 is 1 times 5 plus 2 times 7 plus 3 times 9, which gives me 46. And this one, my answer tells me if it's a 2 by 1 matrix, this is row 2, column 1. Row 2 times column 1 is 4 times 5 plus 5 times 7 plus 6 times 9, which gives me 109. Here are some other examples. If I have a 2 by 2 matrix times a 2 by 3 matrix, the columns from matrix 1 equal the rows of matrix 2, so the resulting matrix will be a 2 by 3. 2 rows by 3 columns. If I have a 1 by 3 times a 3 by 2, that's 1 row by 3 columns and 3 rows by 2 columns, the columns of matrix 1 are equal to the rows of matrix 2, and our resulting matrix will be a 1 by 2. Here we have row 1, column 1, and this is row 1, column 2, and that tells you where to multiply. Row 1 by column 1 goes there. Row 1 by column 2 goes there. We can now talk about the laws of matrix multiplication. We have closure because a matrix times a matrix is equal to a matrix. We do not have the commutative property because A times B does not necessarily equal B times A. We saw that before because the different orders of the matrices, sometimes we cannot multiply them in forward and reverse order. We do have the associative property because A times the quantity B times C is equal to A times B times C. We do have the distributive property. A times B plus C is equal to AB plus AC. We also have this multiplicative identity. In other words, A times I equals A. Well, let's think of that in terms of numbers. If I have 5 times some number, I'll get 5 back. That's what this is saying. Well, for numbers, the multiplicative identity is 1. See, because 5 times 1 is equal to 5, which is the same as 1 times 5 is equal to 5. So that also exists for matrices. I can multiply a matrix by something and get the matrix back. It turns out that I is equal to 1, 0, 0, 1 for a 2 by 2 matrix, and it's equal to 1, 0, 0, 0, 1, 0, 1, 0, 0 for a 3 by 3 matrix. In order to have this identity, you do need to have a square matrix. Here's a square matrix of order 2, here's a square matrix of order 3. Well, A times its inverse is equal to this I. We can see the same thing with numbers. For example, I'll use that same example. If I have 5 times what equals 1? Well, 5 times 1 over 5, which is also written as 5 to the negative 1, is equal to 1. This is the same thing with matrices. Some matrix A times A to the negative 1, just as I had 5 times 1 over 5, or 5 to the negative 1, is equal to 1. I can do A times matrix A to the negative 1 is equal to its identity. The same thing, A to the negative 1 times A is equal to its identity. And what is its identity? For a 2 by 2, it's 1, 0, 0, 1. For a 3 by 3, it's 1, 0, 0, 0, 1, 0, 0, 0, 1.